stoichiometry now. Stoichiometry is a quantitative study. What do you think of when you hear the word quantitative? Numbers. This does have to do with numbers, and it's a mathematical relationship that we're going to be using to figure out stuff in our chemical reactions. Okay? So we're going to be looking at the numerical values, and it is based off of the law of conservation of matter. Okay? Matter cannot be created or destroyed. The law of conservation of matter is the same thing as the law of conservation of mass. Mass is equal on both sides if matter is equal on both sides. So just to reiterate this from the other day, if you didn't hear this, if you have 100 grams on your reactant side, that means you have 100 grams on your product side. You might have, different amounts, like 25 grams is hydrogen, 75 grams is oxygen, but they total up to equaling that 100 on both sides. Just like the number of atoms have to equal on both sides as we are doing in our balancing. If we don't have the right number of atoms, we don't have that, it will not follow the law of conservation of matter, and it will be incorrect. Okay? If you know the amount of one substance, then you can, in a reaction, you can determine the amounts of all the other things in the reaction. All you need is one value, and you can figure out everybody else using math. And they are going to be using those T-charts. We're going to use those T-charts in order to figure them out. Okay? We're going to do moles, grams, we can do liters, and we can do particles here. So anything that equals the mole, we can convert and figure out about any of the reactants or products in our reaction. Okay? But before we can do anything, we have to understand the concept of the mole ratio. The mole ratio is very important in stoichiometry. Without it, you won't be able to do anything. The mole ratio is a conversion factor. Something to something that allows us to switch substances in our reaction. Okay? And it allows us to compare two of the substances. Any two substances, the number of moles we're allowed to use as a conversion factor. However, before you can figure out the moles, you must have a balanced reaction. If it's not balanced, you can't do it. You need moles represented from the coefficients in the balanced reaction. And those coefficients we've been practicing with are now what we're going to use in order to figure out our substances in our reaction. Okay? So, there's a lot of words up here, and you can go back and read them again if you need to. But let's look at some individual problems to kind of put this in perspective. So, on your page, it shows the decomposition of aluminum oxide. I'm going to write it here. We have 2 Al2O3s decomposing into 4 aluminum atoms plus 3 O2 molecules. Okay? So, we're looking specifically at our coefficients. We have the 2 here, the 4 here, and the 3 here. So every time this reaction is run, you need 2 moles of aluminum oxide in order to get it going. You're going to produce 4 atoms or 4 moles of aluminum, and you're always going to get 3 moles or 3 molecules of oxygen here. So this number now tells me 2 moles. This number tells me 4 moles of this. This number tells me 3 moles of O2. That's what those values are telling me in the reaction. And now I can use them as conversion factors. Okay? So, let's see here. You can set it up as a ratio, and as you see in a T-chart, we can set it up like so. We can use it in our T-charts as such, but let's just play around with the ratios for right now. Everybody knows how to write a ratio. 2 to 4 would be like so. We have 2 moles of aluminum oxide going to 4 moles of aluminum. Here, the 4 moles of aluminum going to 3 moles of oxygen. They are now comparable. They are a conversion factor. And the last but not least, if we're doing aluminum oxide to oxygen, it's going to be 2 moles of Al2O3 to 3 moles of oxygen. This is all based off of the balanced reaction. So let's do a couple of examples together now. You must balance these, though, before you begin. So, everybody take a look at number 1. Number 1 is not balanced. What is out of check here? What needs to be balanced? Which ones are not in balance? Cl is not in balance. So let's do that. What can I put here to fix that? Put a 2 here. Good. Who else is not in balance? Barium is Ba, but is it balanced? Do we have the same amounts on each side? Yes, that one's okay. Who is still out of balance? Potassium is now out of balance because we fixed the chlorines. But who else was still out of balance? Our chlorates were out of balance as well. But it's an easy fix. What can we put here to fix them? Put a 2 there. Now the potassiums and the chlorates are in balance. Now when we don't put a number in front, what does it mean? This means an understood 1 here. Okay? So those ones are going to be 1 mole. Okay, in our balanced reaction. So if I'm doing moles of BaCl2, barium chloride, I have 1 mole to how many moles of potassium chloride? How many moles? 2 moles. Okay, over here. Moles of potassium chlorate. How many moles? 2 moles going to how many moles of potassium chloride? 2. So this is a 2 to 2 ratio. Okay? Now I'd like you to try 2, 3, 4 on your own. Then we'll come back in just a minute. Take you like 2 or 3 minutes to balance and do those. Okay, so what did we come up with here? What is the coefficients for balancing for number 2? What do we need here? 1, 2, right? So, moles of H2 to moles of water. 2 moles to 2 moles. 2 moles to 2 moles, right? How about moles of oxygen? Moles of oxygen, 1 mole to 2 moles of H2. How about number 3? How did that one need to balance? What did we need here? Anything? 1? Good. Everybody get those balanced correctly? So, moles of ammonium carbonate, which is this guy. So that's 1 mole. 2 moles of ammonium chloride, which is this guy. That's going to be 2 moles. Okay, so once again, recognizing the ability to figure out names to formulas, that's where that's important. That's why you need to review that Unit 4 stuff. Down here, number 4. What do we got going on here? What are the balancing here? 2? 1, 1, 1. That one was already balanced. It's all ones. Very good. So calcium carbonate is this guy. Calcium oxide is this guy. So 1 mole to 1 mole. Now it's a little bit more practice on the back there. Let's take a look. I want you to do 1, 2, and 3A. Do 1, 2, and 3A. Okay, so let's take a look here. So, first one, what should it be? 1 to 3. 1 nitrogen to 3 hydrogens. How about the next one? 1 to 2. Once again, nitrogen now to ammonia. And the last one. 3 hydrogens for every 2 ammonia. 3 hydrogens every 2 ammonia. All right, now looking at this equation down here. H2 to H2S. What is that going to be? H2, 8, 2. Now, you can reduce this if you like to 1 to 1 because they are both divisible by 8. How about this one? H2, 8, 2, 8S. 1, 8S. Or S8. I meant S8 is what I meant to say. So this is an 8 to 1 relationship. How about H2S? 8 again to S8, which would be 1. So, number 3, answer the following questions for this equation. What is the H2 to H2O relationship, mole ratio? 2 to 2. Good. Now we're going to use this in setting up our first set of conversions. If, suppose you had 20 moles of H2 and plenty of oxygen, so you have plenty of the other reactant, how many moles of water could you make? So we would set up our T-chart just like before. We put our 20 moles in the upper left corner of H2. Now you have to write in the substance into the T-chart. So write that in. And what do we always do when we are doing conversions? What comes next? Drop down the moles, but we also drop down the H2. We have to identify the substance now. So it's moles of H2 that we're putting in there. So drop that down. What are we going to? Moles of, we're going to moles of H2O. So that's what goes on the top. Now we look at our coefficients. We have 2 for the water, so we put a 2 next to the water. We have a 2 for our H2. We put a 2 next to our H2. We multiply and divide. Or, if you want to get snazzy, what can we do to this guy? Simplify it 1 to 1. And we end up getting 20 moles of water as our final answer. Now, some of these T-charts are going to get to be 3-4 steps long, by the way. This one's simple. Mole ratio ones only take 1 step. Okay? So let's do the bottom here. What is the O2 to H2O molar ratio? 1 to 2. Good. Now, let's try that. If we had 20 moles of O2, how many moles of H2O could we make? So, we put our 20 moles O2 in the top corner, just like we always do. We drop down, like you said, diagonal down, those moles of O2. And what do we want here? Moles of H2O, so that's what we're going to put here on the top. And we said we had 1 mole of O2 to every 2 moles of H2O. So the moles of O2 now cancel, and we end up with how many moles of water? 2 times 20 is 40, so 40 moles of water. Okay? So, what now we need to look at is some ones that are not only 1 step. Some of them take 2, some of them take 3. Because on our mole conversion map, you remember our mole conversion map from last unit, you can convert pretty much anything to moles, and you can convert grams, liters, or particles back from moles. So they're not always going to give you moles to start with and moles to end with. They're going to give you grams, liters, and particles to start with and to end with. So it becomes quite a lot of fun. So here, first things first, always write out the balanced equation. That has to happen first. Then we're going to do the step-by-step process of setting up our T-chart. You can read those steps here if you forget. They're right here, okay? So first things first, this is a mass to mass problem. That means we're going from grams to grams. We will be going from grams to grams here. But number one says balance the equation, so we got to do that first. So let's balance the equation. What do we get here? 2, 1, and 2. Is that right? Check it. Good. All right, now let's read our problem and figure out what we've got here. Sodium chloride is produced from its elements through synthesis. Okay, that's what we see here, synthesis. Good. What mass, so we want grams, of sodium is required to produce 25 grams of sodium chloride? So what am I given? I'm given 25 grams of sodium chloride. So that's what I'm going to put in my upper left corner. But I cannot switch to sodium until I have everything in moles. So I have to change my grams to moles first, just like you did last unit. I'm going to diagonal down my grams, and I'm going to go to 1 mole of sodium chloride. So grams of sodium chloride to 1 mole of sodium chloride. How do I find the grams to 1 mole? Where do I need to look? I need to look at the periodic table and get the molar mass. That's what I need to do. Exactly right. So let's do that. What would be the mass of sodium chloride? Na equals what? Off the table. 22.99. Yes, we're going to round everything to the hundredths. Okay, so round it to the 2 decimal places. Okay. And chlorine is what? 35.45, so that adds up to 58.44 grams. So we put our 58.44 down here. Now that we are at moles, we have now, this first step always is change to moles. If it's not in moles, you must change it to moles before you can switch compounds. Now that we're in moles, we can do the mole ratio step. So the next step I call the mole ratio step, right? So what do I diagonal down here? What do I have up here to get rid of? Moles of NaCl. So I'm going to get rid of that now. I'm going to put that down here. What can I go to from moles of NaCl to using my mole ratio? I can go to moles of sodium. All I need to use now is their mole ratio. Sorry, that line doesn't look very good. What's the ratio? How many moles of sodium chloride? How many moles of sodium? Good. So that does my middle section, the mole ratio step. This is the mole ratio part. So first change it to moles, regular mole conversion, mole ratio step. Now, because it wants what? Grams, wants grams, we have to change it back to grams. So 1 mole of sodium equals how many grams of sodium? How many grams of sodium did we say it was? 22.99, so that's going to go here. Now all I have to do is multiply everything on the top. Multiply everything on the bottom, and then divide. And I get my grams of sodium needed to produce my 25 grams of sodium chloride. So, what is that going to be when we calculate it? And if you get real snazzy, what can you do here in this middle step? You can cancel it 1 to 1, right? You can make it 1 to 1. So that makes your calculation a little bit easier. So basically then all I have to do is 25 times 22.99 divided by 58.44. And I end up with 9.834. Now, significant digits. How many are over here to start with? Only 2, so I get to keep only 2 digits. So I keep my 9. What do I do to the 8? Do I leave it alone or round it up? Leave it alone, so it's 9.8 grams of sodium. That is my final answer. Okay? That is what we call a mass to mass. That one takes 3 steps. First, mass, change it to moles. Do the mole ratio, switch compounds. Then change the new compound back to the grams. Or the new element. In this case, it was an element. Let's do one where it's just a 2-stepper, where you only have to do 2 steps. Looking down here, and to speed things up so we're not spending too much time, I'm going to go ahead and balance it for you. Check me, did I balance it right? Does it look equal on both sides of all the atoms? Yes, good, okay. Now, iron 2 bromide, how many moles? We want moles. Moles of this stuff. Needed to react with potassium phosphate to produce 18.54 grams of iron phosphate. That's this guy. So I'm starting with iron 2 phosphate, and I'm working my way over to the iron 2 bromide. And that's going to be my mole ratio step, is between those 2 things. But did it give me moles to start with? No, so I have to change those grams to moles first. That's a pain, I know, but that's what we have to do. So let's do that. 18.54 grams, and this is Fe3PO42. And yes, you're supposed to write the compound in too. It's kind of a pain, I get that. So I'm going to diagonal down, get rid of the grams of Fe3PO42. And I'm going to go to 1 mole of this big compound. So what do I need to do? Go to the periodic table. And I'm going to calculate this one real quick just to save time. And I get 357. Everybody's welcome to check though. 49 grams. Okay, so now once again we had to do that. Change it to moles. Change to moles. Now we can do what since we were at moles? We can do which step? Mole ratio. Very good. Exactly right. So I'm going to diagonal down my moles of my Fe3PO4 here. And I'm going to which one? I want this guy, right? The FeBr2. Now, we have how many moles of FeBr2? 3 goes there. How many moles of our iron 2 phosphate? 1 goes there. And because it's mass to mole, do I need to go any further? I'm done. I'm at moles, right? So that one only takes 2 steps. Now I can calculate. Okay? So 18.54 times 1 times 3, so you can kind of leave out the 1 on top. Multiply the bottom, but once again, one of them's a 1, so you can just divide by the 357.49. And we're going to get our new value. And we get a smaller number, which seems reasonable because moles are usually small. How many digits, though, should I keep in my answer? We have 4 over here to begin with, so I'm going to keep 4 in my answer. 1, 2, 3, 4. Do I round up that last 5 or do I leave it a 9? Good. So this is 0.1556 moles of FeBr2. Is my final answer. And if you notice, the moles of FePO4 cancels with the moles of Fe3PO4, and the grams cancel with the grams. Okay? So what are we left with? Only what we wanted, which was the moles of FeBr2. So, the problems that I assigned you for tonight, though, going over those,